Hi 242. In this video we're going to begin discussing section 13.2, and the material in this section is going to help us begin determining antiderivatives for functions that we currently don't know how to find the antiderivatives of. There's plenty of functions out there that are definitely more complicated than just powers of x or 1 over x or things that like that we already know directly what the antiderivatives of them are. We have to be a little bit sort of, I guess, uh, manipulative here in the way we handle the rest of these kind of problems, because in all of our techniques from now on, we're going to have to be doing some kind of manipulation or changing of the function and the integral itself to be able to figure out the antiderivative. So let's consider an example first, right? So we're going to be let's consider the following. Let's do this. Okay, let's maybe say I wanted to try to find an integral that looked like this. Right? So this says that, remember, I want to find the antiderivative. That's what this symbol means. I want the antiderivative of the function 3x plus 1, the quantity squared. Okay? So this has like some different stuff going on here, right? There's not just powers of x here, okay? And we've got some parentheses here saying that squaring is happening on two terms here, right? It's squaring a binomial, so that's sort of tricky. And so we're not really sure at this point what to do. I can't just apply the power rule to this squaring stuff here, because that rule only applies if it's plain old x squared. And it's not plain old x squared, it's 3x plus 1 squared, right? So I can't apply the power rule. Well, one thing we could do, actually, since this is just a squaring, right, what we could do is actually say, well, I could remove the parentheses. I could do what the operation is telling me to do, which is actually square this thing out, right? So let's maybe consider one of our options here. So maybe like option 1. We'll call this option 1. Okay, option 1 is actually to perform that squaring, right? Because I could rewrite this as the integral of, let's see what happens when I square this. When I square out this binomial, I would get 9x squared plus, that's from the first term, right? 3x times 3x, plus outside is 3x and inside is 3x, so that's plus 6x plus, and the last term would be 1, because 1 times 1 is 1. Okay. Again, that's the result of squaring out that 3x plus 1. Notice when I did that now, I now have powers of x everywhere in constants, and I know that the integral, this antiderivative process, can just work term by term. So I could actually perform this now, right, to reverse the power rule here. The 9 just goes along in the front as a constant. The antiderivative of x squared is x to the third over 3. Next term, plus 6 is just a constant in front of an x, so 6 times antiderivative of x is x squared over 2. I'm reversing the power rule. Plus the antiderivative of 1, if x is the variable, that's x, and we don't forget our big plus c for our constant of integration. Okay, yeah, we could make this look nicer, right? This is 3x to the third plus 3x squared plus x plus c, right? Okay, and that's a perfectly valid way to handle this, right? And like I said, that's option 1. The second option will be the topic of this video, right, which is an alternative. But you might be thinking, well, that wasn't so bad, right? Why can't we just do that every time instead of maybe learning this new topic that this video is going to be talking about? Well, I can exactly point out why, because what if I slightly change the problem so it said something like this? Aha! Now you're not feeling so confident, right? Because now you're thinking to yourself, okay, well, if I wanted to get rid of these parentheses here, I'd have to multiply 3x plus 1 by itself 75 times. And I'm pretty sure that there's nobody listening out there that wants to do this. I don't even want to do this, and I really love math, right? So this is a perfectly valid option up here if the power right here isn't too big. Okay, but what do we do if the power here gets big and we're like feeling a little lazy and we don't want to do that, right? We don't want to do out all of this foiling and stuff, right? Okay, well, one thing we can do is what's covered in this video, which is what's called make a substitution. Okay, so let's take this problem to a new page so that we have a little bit more room. So what have we got here? 3x plus 1, and then we raise that thing to the 75th power. We can keep that big power there. Okay, so let's see, we had 3x plus 1 to the 75th power dx, because x is the variable, remember. Okay, well, what we do is to make a substitution. What we can do is change a variable, right? And this is going to be our technique for this section, which is called the technique of substitution, right? So we're going to be doing what's called a substitution. Okay. And in this process, what we do is we rewrite the entire integral so that it's no longer using x as a variable, right? What we want to do is transform this integral into something we immediately know the antiderivative of, okay? So we want to somehow do a transformation here. Okay, well, if I want to make a transformation and make this integral use a different variable, right? I can't use x anymore because x has already been used. Okay, then I need to use a different letter, right? I need to choose a different letter. Okay, and conventionally, when you're performing this technique of what's called substitution, most calculus textbooks and most math people will use the letter u for this substitution. Okay, and so the idea here, let me just lower our little box here. Okay, to perform this sort of integration by substitution, like I said, we want to change the variable in the integral so that we simplify the integrand. Remember, that's the thing inside we're finding the antiderivative of. We want to simplify that integrand, the function itself, down to something we know the antiderivative of, right? Okay, so let's maybe walk through the process here, and then we will maybe do a few more examples after that. Okay, so how this process works is to locate the trouble spot first, right? The trouble in our problem here is that we have something besides plain old x or a variable, right? Something inside of these parentheses being raised to the 75th power, right? That's our trouble spot right there. Let me underline it for you in a color. This is our trouble spot right there, right? If this just said x to the 75th, we would know immediately what to do. Or if this said u to the 75th, we would know what to do, right? If it was just a single letter in here. Well, if that's the case, if we knew what to do if that was a single letter, then let's make that our substitution. So in step 1 of our method here, we choose a substitution for u, and u is going to be an expression of x. That's all that means right there, right? U is an expression of x. And that choice needs to simplify what's going on in this integrand, in the function itself. Okay, so let's do step 1. So step 1, okay, we are going to let u equal, remember it's an expression of x, and that's all u of x means, right? Okay, this thing is saying u is shorthand notation for u of x, right? So we're just emphasizing here that u is going to equal some kind of x stuff, right? So we're going to make u be that ugly stuff inside those parentheses because that's our trouble spot. Okay, that's our first step. Okay, now what's step 2? Let's see what step 2 is. Says express the entire integral in terms of u. Let's think about what this other stuff means for just a second. But if I want to rewrite everything in this integral in terms of u, that means this inside stuff here, this 3x plus 1 is u. The 75 is just a power, so it's fine. But there's this troublesome dx thing over here, right? This dx thing. If this stuff inside of here is going to be in terms of u, that dx cannot stay there, right? Because if I'm changing my variable to u, then this somehow needs to be saying the variable is u, right? This needs to somehow become a du, right? So let's notice for a second that, so let's make ourselves a little note here. Okay, let's notice for a second that we have a relationship between u and x right here, right? We know that u is 3x plus 1. Okay, let's think about this for a second. If we write u prime of x, right? Notice that u of x is this expression right here, right? We're using function notation there. Then u prime of x is what? The derivative of that thing, right? There's an alternative way we could write that, right? U prime of x could also be written as, if you remember this, du dx, right? Those two things say the same thing. It says the derivative of u and x is the variable. The derivative of u and x is the variable. Okay, these two notations are the same, Okay, but something you probably didn't know is that the du and the dx, they can be like separated from each other. So that means I can rewrite this expression here that we have, this equality here. I can write this as u prime of x dx equals du. Okay, so those two lines are still the same thing. All I did is multiply the dx up with the u prime of x. Okay, so I now have du equals u prime of x dx. Okay, and that's just because of the definition of the derivative. U prime of x dx in terms of notation is du over dx. Okay. All right, so how does that actually help us? Well, this helps us because what we're able to do is figure out how to write a du, right? Remember I told you that we want to write a du right here somehow, right? Well, notice that du is equal to u prime of x dx. So all I have to do is write the derivative of u here and put a little dx next to it, and that's equal to du. For our example here, we can make this step 2, I guess, if you like. Okay. What that means is that I can write, what is u prime of x? U prime of x is the derivative of this u stuff, right? That's what u prime of x means. It's the derivative of u of x. U prime of x, the derivative of this thing right here, is 3, right? U prime of x is 3. So that means I can write 3, or actually if you want to write it a different way, how about we write it like this? Just so that you can see exactly where this is coming from, right? We can write u prime of x is equal to 3, right? And if you like seeing it like this, right, then du dx is equal to 3. Okay? And again, we can move that dx up there if we like, so du equals 3 dx, right? Good. Okay, so if I at least have a way to write du, that's good, right? So notice that du is 3 dx. Okay, so now what I need to do is try to complete step 2 by expressing the entire integral we have in terms of u and du, right? I want to write blah blah u here, u to the 75th, and then I want to somehow have a du right here. Okay. Notice that a little note here says all terms involving x and dx have to be replaced with terms involving u and du. Okay, so let's start a new page and I'll sort of summarize what we've got going on here at the top. Okay, so we have the integral that we're working with is 3x plus 1 to the 75th, and we've got this dx. And remember that for our choice for our substitution, we said that u is equal to 3x plus 1. And then we notice that u prime of x, or du dx, is equal to 3, right? Again, the derivative of u with respect to x is 3, right? Okay, so again, rewriting this means that du is equal to 3 dx. Okay, good. But we don't actually have a 3 dx here, right? We just have a dx. I could replace dx with what? Well, notice if I divide both sides by 3, I would get du over 3 is equal to dx. Okay, so now what I can do is rewrite this whole thing. Okay, so let's rewrite this integral. Rewrite. Okay, I'm going to rewrite the integral, and this inside stuff here is u. That's u to the 75th. And what is dx? Remember, dx is du over 3. Okay, great. Well, this may look still not too great, but let's think about what this over 3 means, right? That's a fraction, okay? But what I could do is make this maybe a little more clearer by writing this as u to the 75th times 1/3 du, right? Okay, because this 3x plus 1 to the 75th, that's joined with a little dot right there with the dx, right? Okay, they're sort of together, all strung together like that. So if I have this 1/3 right here, it's just a constant. It could be brought out front. Okay, so it could be written as, this could be written as 1/3 integral u to the 75th du. And now we actually do know what to do with that in terms of an antiderivative here, because I can do the antiderivative of u to the 75th. 1/3 u to the 76th over 76 plus c, of course, right? But I can't leave it like this because our original integral was written in terms of x. So for our last step here, what we have to do is evaluate it, we just did that step 3, and replace u with our substitution from step 1. Okay, so our final answer here would have to be to rewrite this 1/3 here like this. as 1/3 3x plus 1 to the 76th over 76 plus c. And now we're all done. We'll do more examples in the next video.